In practice, we have a test that's a little bit easier to use than the direct comparison test. This is going to be the limit comparison test. So we're going to have our sequences an and bn all positive. If the limit as n goes to infinity of an over bn is equal to a number which is non-zero, then the series for an and the series for bn are either going to both converge or both diverge together. What will make this test a little bit nicer than our direct comparison test is that we don't have to fuss around with the inequalities. So this is a little bit easier to think about. So let's redo our examples. Our first example was a sub n equal to 1 over n squared plus n plus 1. What we did before is we kind of squint at this thing, and we notice that the thing that's really going to look like something that we already know how to do is 1 over n squared. If I let b sub n be equal to 1 over n squared, that's going to be a p series, and it's going to converge since p is equal to 2. The p here is bigger than 1, so that's in our range of convergent series. So I'm going to take the limit as n goes to infinity of an over bn. So we put our an and our bn in. We're going to clear out the denominators by multiplying by n squared times n squared plus n plus 1 over itself. That's going to leave me with n squared on top and an n squared plus n plus 1 on the bottom. Okay, you have your choice of how you clean this up. I like to divide top and bottom by n squared, which will give me a 1 on top, and then 1 plus 1 over n plus 1 over n squared. 1 over n goes to 0, 1 over n squared goes to 0, so our limit's going to be equal to 1. What does that mean? Well, the test says we have an L equal to 1. It's non-zero, not infinite. So that means these two series either converge or diverge together. Since b sub n converges as a series, that means a sub n has to converge also as a series. So our series converges. For our other one, which will be an example where we have divergence, let's see. We have a sub n equal to 1 over n to the 1/3 plus 6. Again, I squint at this, and we know we're looking at b sub n equal to 1 over n to the 1/3. We tried using that with the direct comparison test, and we wound up not being able to use that because we couldn't make the inequality work out right. In this case, we'll actually be able to work with this one. So let's take a look. If I go with 1 over n to the 1/3, again, I have a p series. So we're looking at a p series with p equal to 1/3, and that's in our range for divergence, between 0 and 1 with 1 inclusive. So the series for 1 over n to the 1/3 is divergent. We take the limit, n goes to infinity of an over bn. Same idea, we write them out, and now I'm going to clear the denominators. Multiply by n to the 1/3, n to the 1/3 plus 6 on top and bottom, and clear things out. So it's going to leave me with n to the 1/3 over n to the 1/3 plus 6. I'm going to multiply top and bottom by 1 over n to the 1/3 just to reduce this. So I'll get a 1/3. I'll get a 1 up on top, a 1 for this term, and then a 6 over n to the 1/3 over here. As we let n go to infinity, we're going to get 1 over 1 plus, and then this thing's going to go to 0 because our n is in the bottom with a positive exponent. So we're going to have our limit equal to 1. So that tells me the series for an and the series for bn are going to both diverge or both converge together. Since bn diverges, that means an, the series for an, also has to diverge. Why is the limit comparison test true? Because of the direct comparison test. Let's take a look. We're assuming limit an over bn is going to be equal to L. Non-zero, not infinite. Now, we're taking a limit, so let's look at the picture. What's happening here is I'm going to take my interval small enough so somebody gives me an epsilon, and I fix my interval around what we're calling the limit L. That's going to mean for big enough n, I'm going to have all of my an over bn's trapped inside of this interval. That's from our definition of limit. Now, if they're all trapped in here, I can just make my interval small enough so that we're far away from L plus 1. So that's just saying when I get big enough n, they're all trapped in this interval, If you're trapped in this interval, you're less than or equal to L plus 1. Just this statement here. We have bigger than 0 because we're using AN and BN bigger than 0 too. I move the BN to the other side, and then you notice this is the setup for direct comparison test. Direct comparison test is going to say if the series for BN converges, then the series for AN is also going to converge. Also, if the series for AN diverges, then the series for BN is going to diverge also by direct comparison test. So what we have here is, what are we unspooling? We're unspooling half of our final statement for the limit comparison test. How do we get the other side? Well, to do that, note that we have L is not equal to 0, so that means I can flip it over. When I do that, I'm looking at limit as n goes to infinity, Bn over An equal to 1 over L, not 0, not infinite. So I just repeat the same argument. I'll use an n prime just because the n's will be different. We have Bn prime over An prime, 1 over L plus 1. Same argument I use here, except wherever I had an L, I replace it with a 1 over L, and we just switch where Bn and An are in the fraction. Now this puts Bn in the middle of the inequality, so we could pull out our direct comparison test, but we just switch the An and the Bn in the statement. So now it's going to be the outside one, which is An, converges. Then we're going to have the series for Bn converging by direct comparison test. If we have that series for Bn diverges, Bn being the one in the middle now, then the series for An is also going to diverge by the direct comparison test. So let's see what we have. If I take the first statement here, the first statement here, that's going to say that series for An, series for Bn converge together. If I take the statement here and the statement here, that's saying that An and the series for Bn diverge together. So direct comparison test just leads us right to our limit comparison test.